By the end of this video, we will understand how to mentally solve reliability questions with logic instead of mathematics. Let's get started. You are given a system has 9 independent components 1 to 9. P subscript I is 75%. It is the probability that ith component is functioning. The system structure is as pictured in the figure below. A new component with probability of functioning equal to 0.95 is available to replace one of the current components. The goal is to maximize the improvement of system's reliability. Determine which one of the following components should be replaced to achieve the goal. So for this problem, all you need to know is how to read system structures. I would say terminology-wise, the only thing that might be helpful is to understand the difference between sequential versus parallel. And that's mainly just so you can understand me talking through the solution. I have this in other videos as well, but just jumping up here, sequential just means that before you even get to, let's say, component 7, you have to get to this point in the structure. So there's some component to the left and then some component to the right, and both of them are in sequence. That is, they both need to succeed for you to succeed overall. That's as opposed to parallel systems. So 7 is in a parallel system with 8 and 9. So let's say you managed to get to this point. In order to get to the end, you either need to be able to have 7 succeed, or you need 8 and 9 to succeed. And then obviously if all 3 succeed, you also will get to the end of the system. So that's just how to go about reading this structure and the difference between sequential versus parallel. So actually with that, we can just jump right into it. I would say at this point, reliability questions, at least as far as the level of complication or complexity that arises in MAS1 questions, I would say is actually pretty standard. So I know in the coaching actuaries formula sheet, there's a ton of reliability formulas, but really to me, I think what's most important is just that you understand the terms. So sequential versus parallel, it's not in this video, but in other videos we'll talk about minimum path sets or minimum cut sets, and really all you need to know is what those terms mean. And if you do, then you can actually kind of reason through the mathematics on the fly. I've found. So I wouldn't worry too much about memorizing all those notations. If you just understand what the terms mean, I feel like reliability theory questions are actually pretty straightforward. So for this question, I'm going to first go through brute force mathematics. This is not how I'd recommend doing the problem. Just wanted to go through the math itself, just so we have that. And then after that, I'm going to walk through how I actually solve the problem, which is really just kind of thinking through the visual and intuiting the solution. So first off, reliability is just equal to 1 minus failure. So whether you get from the very beginning to the very end or not is the same as 1 minus the probability you don't make it to the end. And then I have this system A versus system B. So I am just using that as a shorthand for system A is this kind of first sequence, and then system B is this second sequence. So for system A, the probability of it succeeding, and sorry, not system A, this is the probability the subsection A succeeds. So that is equivalent to 1 minus the probability that that system fails, and that is equal to the product of all of those individual failures. So to go back up to this image, the only way you don't get from this point to this point is if 1 fails and 2, 3, and 4 fail, and 1 fails, 2, 3, or 4 fail, and 5 or 6 fail. Right? Because it's okay if 2 and 3 succeed but 4 fails, you don't get through to the next checkpoint. So this is just saying the failure of the sequence of just 1, the failure of the sequence of 2, 3, and 4, and that can happen in a number of different ways, and then the failure of the section 5 and 6. And so then finally, we actually go back to another 1 minus. So here we're saying, subbing in instead of the failures, the probability of the system 1 failing is just 1 minus that part succeeding. And that's just kind of me being consistent. That's not really helpful. But once we get to this part, so in order for that branch to succeed, or excuse me, fail, that's the same as 1 minus all of them succeeding. So what's the probability that part 2, 3, and 4 work? That's the only way you can get through that branch, and then 1 minus that is the probability you don't get through that branch. And then likewise for 5 and 6, it's 1 minus the probability of them both succeeding. So you'll see this a lot with reliability theory questions, that you're going to really need to think about when it makes sense to do 1 minus the thing you care about. So you'll notice we jump from success to we want to convert things to failures to we want to convert things to successes. So pretty much if you can ever avoid doing a combination and choose K calculation, avoid it. So that's why we're constantly doing this. Okay, we care about the reliability, which is a success. Okay, well, now let's convert successes to failures. Oh, well, now let's convert these sub-failures to successes. So that's why we're doing that, just to make the math simpler. And then for the second sequence, it's the exact same process. So assuming we got to this point, just ignore everything to the left. What's the probability I get to the end? And that's going to be equal to 1 minus the probability of succeeding on part 7 multiplied by 1 minus 8 and 9 succeeding. So the probability of that subsequent subset failing. So finally, we have the reliability is part A. You get from the beginning to that checkpoint, and then you get from that checkpoint to the end. It's just the product of those probabilities since they're independent. And this is just copying and pasting what we have up here. So at this point, we can then say, well, every single one of these parts, S subscript I, is 0.75. And then the question is, well, if we replaced one of them with a part with 95% success rate, what would maximize the overall reliability? And so here I have none, so if we just plug in 0.75 for all of them, it's reliable 83% of the time. And then, okay, well, I'm going to change this value instead of 75% to 95%. What happens? It becomes 87.9%. So I do this for all of the different parts, and you see they're ties. So 3, 4, and 5 were in sequence with one another. In order doesn't matter since they're independent. And so this is just all the same reliability. And then when we plug all those values in, we see that 7 has the highest number of 91%. So 7 ends up being our answer. So that took us, 6, 7, 8 minutes to figure out. There's actually a really quick way to reason through this problem without having to do any math. If you're familiar with the Monty Hall problem, there's 3 doors and 2 goats and 1 car and yada yada yada. These types of problems I like to take to absolute extremes, and I feel like that typically makes them simpler. So from Monty Hall, if you picture that with 1,000,000 doors instead of just 3, the answer and why the probabilities work out to be what they are makes a lot of sense. Similarly with this problem, we can do the same thing. So right now it's kind of hard to intuit because, we have 1, 2, and 3. There's not a lot of difference, and it's difficult to just know what is right. But we can break this problem up into 2 parts. So one part is it better to be in a 3 stack of parallel system or a 2 stack of parallel system? And then also we can say within a parallel system, is it better to be in a 1 sequence or a multiple sequence? So here I have this just built out to ultimate, you can picture green instead of only having the 10 lines. Imagine there's a million different parts, and blue only has one. So what's the probability that I get from the beginning to the end if I make this one green line a little bit better? Chances are it's not going to make a big difference, right? Because even if I said this part is 100% failure rate, just make it absolutely useless, I'm probably still going to be okay because it's a parallel system with all these other parts. I'll probably get through just fine. However, this blue part is crucial, and without it, I am screwed. So I know if I have this really large parallel system or a really small parallel system, I get a lot more benefit by improving the blue line versus the green lines. So going back up to the question, it's 3 versus 2, but I know that the smaller set is what's important. So in this case, I'm probably going to end up with something on the right, not the left. So then the next question is, okay, let's say I know it's going to be 7, 8, or 9. Is it going to be 7 or is it going to be 8 or 9? At this point, you can just take the shortcut and say they're tied, so it should be 7 or something like that. But I think even the solution kind of accounts for that by not offering 8 and 9 as options. So now let's take this one to an extreme. Instead of it being 1 or 2 parts, let's say it's 1 or many parts. Again, same line of reasoning. You can just think, if I make one of these parts, twice as good, does it really help me? No, because there's so many chances of the sequence failing. There's so many moving parts. Chances are one of them is going to break, and if I make one of them better, it's not going to help me that much. But if I improve the blue part, that's just a one series sequence, and so if this gets better, the system's going to immediately kind of feel that benefit. So I'm not sure if this is helpful, but maybe this is too high level and I just got lucky. But I really feel like this is a problem, and I think it's somewhat common with the reliability questions that you can just kind of reason through these systems on what the answer is. And that's how I ended up selecting 7 without doing any of the math. So scrolling back up, just to figure out the letter, 7 corresponds to D. So D is the final answer. If you find these videos helpful, I'd really appreciate it if you subscribe. Lets me know that you find these videos helpful and I should continue making them, so please consider doing so, liking or commenting below. Thanks, have a good one.